Hey Brandon, what would happen if you drop two pieces of toilet paper, both at the same height, but one is rolling and one is being dropped normally?
Well, they're gonna fall down at the same time. What else could happen?
I knew you're stupid. The one that's rolling would fall down slower than the one that's not rolling.
What? That doesn't even make sense.
You sure?
Yeah.
Well, my mom just went out to buy some toilet paper, but until she comes back, I can prove it to you using conservation of energy.
What? You can't even prove it using energy. The only way you can prove it is using forces.
Do you even pay attention in class?
Yeah, when I'm not sleeping.
Okay, fine. I'll prove it to you using forces. Try to keep up with me, little boy. Okay, so here's my proof. So for free fall, using the kinematic formula, delta D is equal to V delta T plus 1 over 2A delta T squared. And we know that time, if the time is the same, delta T is equal to the square root of 2 delta D1 over G. And for rolling, the time is equal to the square root of 2 delta D2 over the acceleration of the rolling thing. And then from there, because you know that time is the same, you basically get D1 over D2 is equal to G over A. So using the parallel axis theorem, aka PAT, we know that the inertia is equal to 1 over 2 m bracket inner radius squared plus 3 times outer radius squared bracket. And this is our equation number 2. So here's a free body diagram. This is the toilet paper, rolling toilet paper. So there's the force of tension pushing it upwards, and there's the force of gravity pushing it downwards acting. So here we solve for alpha. So we know that torque is equal to I alpha, and because using PAT we know I, so we substitute 2 into torque is equal to I alpha, and so that's how we know that I alpha is equal to mgr over 1 over 2 m bracket inner radius squared plus 3 outer radius squared. So here we solve for A, and because A is equal to alpha r, we multiply this by r. So now we know the acceleration. So we substitute this equation into the very first equation we get here. So we know that delta D1 over delta D2 is equal to G over 2gr outer radius squared over inner radius squared plus outer radius squared. So from there we get delta D2 is equal to delta D1 over 3 over 2 plus inner radius squared over 2 times outer radius squared at m.
Yeah, anyone could put a bunch of numbers together and say it's right. I want to see a live demonstration. Prove it.
Well, it's a good thing my mom came home. Now we have 2 toilet papers to test out this. So, measuring the inner radius is 2.1 centimeters, and the outer radius is 6.5 centimeters, and according to my calculations, if the non-rolling one is dropped at 2 meters, that would mean the rolling one has to be dropped at 1.25 meters.
See, Angus, I told you need to drop them from different heights, so that when they land, they'll hit at the same time.
No, you said you have to drop at the same height, and you said it would take the same amount of time for both of them to hit the ground.
Yeah, I only said that because I was taking sources of air into account.
Like what?
Like air resistance, human errors, and the radius of the toilet paper slightly changing as it falls down.
Yeah, but that barely affects it.
Yeah, that's what I was saying, that the toilet paper that's not rolling will have to be dropped from a much higher height than the toilet paper that is rolling.
Whatever, as long as you understand.